Hey students, I got a question here. It actually comes off the quickie quiz, so it's not really a homework problem. And then I thought I would do the second one just to kind of fill this in. But there's some nice conceptual ideas that I thought I would review a little bit, and if that helps. So let's talk about this. It says the hydrogen atom is in its ground state. And incident on the atoms are many photons, but each of them have this energy of 10.5 eV. What is the result? And they give us three options. They say the atom is excited to a higher allowed state, the atom is ionized, or the photons pass by the atoms without any interaction. So let me do a little energy diagram. This is this kind of this one-dimensional graph, kind of like a bar graph or a pie graph. And it only focuses on the energy. Now, the equation that was worked out in this section, and this is actually from section 42.3, they go through and show that the energy of the different quantized levels in the atom would be this little formula, negative 13.6 electron volts divided by n squared, where n equals 1 is the ground state, then n equal 2 is the first excited state, n equal to 3 is the next excited state, and on to infinity. So if you look at these, the lowest level would be somewhere about here, negative 13.6. And so my axis here, this line I'm drawing, is something actually more negative than 13.6. The next energy level then would be when we have a 4 in there. Let me grab my calculator. So 13.6 divided by a 4 would be a negative 3.4 electron volts. And maybe I'll put here to the side n equal 1, n equal 2, n equal 3, and maybe I'll just go to n equal 4. That's what I did in class. Okay, so the next energy level, 13.6 divided by 3 squared, is a negative 1.51. And then finally 13.6 divided by 4 squared is then negative 0.85. And you can see, in fact, they probably should be drawn closer together than this, that the energy levels, number gets smaller. But as n approaches infinity, so there's an infinite number of them, we get closer and closer to 0. And so the n equals infinity, if you will, has an energy of 0. So this is higher energies. And I'll just comment that, we're using the same kind of idea that we did with gravity and our astronomy and our rockets, where we would, label 0 energy as being really far away in terms of potential energy. And so this is what we call the ionization energy. You give it so much energy, the electron gets further and further and further away, if you will. Though a wave, it just gets more wiggly, and eventually it wiggles away when it gets enough energy. And enough energy is 0. And so that's the ionization. Now, it's probably also nice to, maybe I'll do this in a different color so it'll stand out, to look at these differences. And so 13 minus 3.4 would be 10.2 is the energy between the first and the second. And then here, if I go, what is that? 3.4 minus 1.51 is 189 electron volts. Or this whole thing here is then adding to the 10.2. And so let me pause here for a moment. I know in class I focused a little bit more on the electron going from excited states down because they would emit photons. So if we look at electron in a level number 3, what that would say is it could lose all of its energy, that would be 12.09 electron volts, and create a photon with that much energy. But it also could do something like this. It could lose some of its energy going from 3 to 2 and then make a photon of 1.89, and then at 2 go on down from 2 to 1, making another photon. And so as this cascades down, it either has one large energetic photon or two, and this one's actually pretty energetic, and then reasonably energetic. This is actually the visible range. In fact, that is our Balmer series. This would be that red one. This would be the alpha line. And so there's our energy in the red. Okay, now what I didn't focus too much on in the lecture, and kind of want to explain that now, is the reverse is also true on absorption. And so the only way you're going to get to level number 3 is if you hit it with a 12.09 electron volts photon, or you first hit it with a 10.2 and it's kind of hanging around on this next level, and then you hit it with a 1.89. Now, I don't know if it's needed. Maybe I'll just do one more here. What is 1.51 divided by 0.85? There's a small amount of energy here between 4 and 3. That would be in the infrared. Is that the Passion series, I believe? Or we could also talk about the whole thing. But I don't think we need to keep talking about the numbers here to really kind of answer this question, because here's the question. It says it is then shot out with photons of 10.5. See, nothing matches 10.5. And they want you to realize the electron has to go into some energy state. It can't just go and hang out at some non-energy level. It doesn't exist. That's impossible. And so it can't just grab the 10.5 and even sit there temporarily, if you will, and then jump up another 10 and get some positive energy here. Because if we do 10.5 twice, that's 21 electron volts. And if you hit it with a single photon of 21, that's quite possible. It just goes from here way up to all these energy levels that aren't quantized. Remember, it's only quantized when it's in the box. So once it gets ionized, it can have any energy level it wants. And so to get completely ionized, you would have to hit it with 13.6, or actually anything above 13.6, because then the extra energy is possible, and that just becomes kinetic energy. There are no quantum levels there, because again, as we said, the concept of the quantum mechanic is the wave nature, and the waves are quantized, but they're only when you put them in a box. So as long as the electron is trapped within the atom, we've got quantum levels, but once it's free, you don't have those. So had they said this was a photon of something greater than 13.6, I would have gone with answer B, the atom gets ionized. Any value, that's what would happen. Or if they had given me 10.2 or 12.05, I would have said, oh, it gets absorbed and the energy gets up to an excited allowed state. That would be A. The atom gets excited to a higher allowed state. And if they only gave me a photon of 1.89, I would say, well, that's really not going to do it either, because that can absorb it, but only when it gets up to number 2. And if they're all just sitting in this gas of hydrogen, they're all at this ground state, this option's not available. They would have to first absorb a 10.2, then they could absorb the 1.89. In fact, that kind of reminds me of those transition lenses, where this energy level then is so high that it's in the UV. So when you're inside of a building, the electrons that are in your glasses, if you have transition glasses, don't actually jump up to there. And because they're not there, they can't absorb some of the visible light. And so the light Visible light goes right through them. And so your glasses look nice and clear. But as soon as you walk outside, the UV light gets them excited up to this level. Now at this level, they can absorb stuff in the visible. And so now they start absorbing a lot of light in the visible because they've got the UV from the sun. And now they turn kind of a dark color because they're absorbing it. And that's why they call it transitions. And so this is kind of taking advantage of the quantum effect and making your transition lenses. But sorry about that. I digress from the question. And so A and B just don't work. And the thing that is C here is that the photon just passes by the atom. There's no interaction. You can't absorb it. You would violate conservation of energy. You can't like absorb it and say, well, we'll just take a little bit away because it's more than. It's not like you're buying something at the store and you go, well, as long as I have either that much or more, I can buy the product because I can just pocket the rest of the money. But it doesn't work that way. You can't pocket the extra money. It's got to go somewhere. And it doesn't have that energy level. Now, I suppose, and it reminds me of my research days, it's statistically extremely unlikely. But in a rare case, you might have, here's the atom, here's the electron, and a photon and a second photon actually hit the same electron at the same moment, thereby transferring a full 21 electron volt, which, as we said earlier, would energize it and give it some kinetic energy. So technically that could happen, but it is so rare. These electrons are really small. These photons are really small. And getting 3 of them to come together at exactly the same moment is extremely rare. And I remember actually doing my dissertation, and I guess this was a subset of my dissertation, but we were working, I think it was Hughes Company, and they wanted us to kind of study a double photon absorption. And so what we ended up doing, just to see if we could see it, of course, first we calculated what are the odds, and they were really low. And so we just said, well, what if we have more photons? And the more photons you have, the more likely it is. And so we ultimately saw it, but we saw it when we would take a laser, and that was 10 megawatts of power shining at this thing. So yeah, 10 megawatts of power seemed to get enough photons in here, but this is a small power plant. It is highly, highly unlikely. So let me just kind of throw that away. And that, again, this is just not going to be a double photon absorption. So again, best answer right there. The photon passes right by the atom, doesn't interact because you cannot conservation of energy. So that was the main question. Hopefully that helped. But I thought, well, as long as I'm doing a quickie quiz, why don't I jump down here and do number 2? Here it says a hydrogen atom makes a transition from level 3 to level 2. So this was what I was talking about earlier, level 3 to level 2. And then it makes a transition from level 2 down to level 1. Okay, so in other words, it would release a photon of this much, which, as I said, this would be the alpha line of the hydrogen atom, and then this would be in the ultraviolet. Which transmission results in the emission of the longest wavelength? Well, remember, the energy of a photon is hc over lambda. So big wavelengths mean low energy. So 3 to 2 is a way bigger wavelength than this one. In fact, maybe I'll calculate it here. I know that's not the question here, but I think we've answered the question. The first transition, yes. The second, no. Neither, because the wavelengths are the same. No. And so it's this first transition. And I think the point of this problem is not really to do a calculation, although I will. The first of the point of this little quickie quiz here was to try to get you to see this relationship and how the energy levels are getting closer together. And so transitions that go 2 to 1 or anything up here down to 1 would be in the ultraviolet. Anything that would be from 3 to 2 or anything up here down to 2 would be in the visible, although at some point, because I think this is the Balmer series. It's pretty popular. The 3-2 is red. The 4-2 is kind of that turquoise. The 5-2 is a blue. The 6-2 is a violet. And now 7-2 gets us into the ultraviolet. So you would only see 4 of them. But the point is, anything above it down to 2 would be very close to the visible range, which is these 2 and 3 and 4 EVs of energy, which then as they get closer together, anything above 3, so 4-3, 5-3, 6-3, very little energy. None of those would be in the visible. Those would all be in the infrared. No visible, no ultraviolet. And so the spacing is real close together. And I think that's the point of the problem, for you to realize the 2-3 would be closer, significantly closer, as you can see, a 2 compared to the 2-1, which is I'll call it a 10. And so this is 5 to 6 times bigger. And that's what they want you to recognize. Now I'll finish a little video with actually doing then the calculation. And so if we say E equals to HC over lambda, we can write this as HC over E. And here we can do it in whatever units we want. I think in class for you guys, I focused more on H being 6.63 times 10 to the minus 34. And those are your base units in joules seconds, and C being 3 times 10 to the 8 meters per second. And so if you put your energy in joules, all this is going to come out to be meters. But a very nice number to remember is, I'll just throw this out, the quickie quiz, is if you change your energy from joules into electron volts, and you change your speed to nanometers per second, this converts to 12.42 electron volts per nanometer. And what's nice about that is then if you put the energy, which in my case I'll put 1.89 eV for the transition from the 3 to the 2, the EV cancels off, 3 to 2, and you get your answer in nanometers. So 1242 divided by 1.89 is 657 nanometers. And as I said, this would be the hydrogen alpha line. It would be red. Getting close to that 700, the far end of the spectrum. And if we do the same logic for the transition from 2 to 1, which is this HC over lambda, and I will use the 1242 electron volts times nanometers, and then this, energy. And then coming back to here, the energy of this transition is the 10.2. So 10.2, if it was an even 10, you're looking at only 124 nanometers. It's going to be a little less than that. And so I'll just call it 122. So 122 nanometers. And again, like I was saying, this will be in the ultraviolet, way into the ultraviolet. And so that's our transition from 2 to 1. So again, which one has the longer wavelength? Definitely the 3 to 2. All right. Take care, everyone.